All right, so obviously this section is on buffers, so let's get started. Okay, so there's a few definitions for you there which aren't really going to make much sense, I guess, until we start actually going through this stuff, but you can go back and look at these because they're a reasonably good summary of what's going on. A lot of students get confused with buffers, but basically if you keep in mind that a buffer is just basically an equilibrium, it's an equilibrium with an acid and its conjugate base, and it operates according to Le Chatelier's principle. At least in qualitative terms, you can't go wrong. Let's just move on to the next slide. Now, let me just show you how this works. So, in this case, I've got acetic acid. Where'd my... Oh, there it goes. I've got acetic acid here, and I'm dissolving it, or it's in solution, and it's in solution with... where did my pen go? Oh, now it's back here. Anyway, so I've got acetic acid, and it's reacting with water. And basically, as you know, this is a weak acid. It won't be that much ionized, but it will be a little bit. And we've got an equilibrium going on here where we've got this acid's conjugate base, and of course, this acid could then react with the conjugate acid of water, which is hydronium ion, and the reaction can go back in the other direction. So there's our equilibrium. Well, so what? Well, the rest of it just boils down really to Le Chatelier's principle. And so what I've done here is I've said, okay, let's take the simple example. Let's say we add acid to this system, another acid. Let's say it's HCl, something really strong. So for all intents and purposes, what you're doing is you're adding H+, which is then, of course, forming hydronium ion. And, of course, that hydronium ion concentration is going up. Well, it's an equilibrium. If the hydronium ion concentration is increasing here, then the equilibrium will move to try to counteract that imposed change. That is, it's going to move towards the left to try and decrease the amount of hydronium ion. So what you could say is that this system buffers against an addition of acid, that is, against a decrease in pH. Well, what about the other way around? What about if we add base? Well, if you add base, and this is the simplest way to look at it, and it's easy to get confused with this stuff. There we go, I've lost my pen again. Not as confusing as dealing with the pen. If I add base, then what you can say is that what's happening here is you're actually getting this reaction going on where you're using up H3O+, and so therefore you would expect the H3O+ concentration to be going down. So if that's going down, according to Le Chatelier's principle, the equilibrium will move towards the right to try to counteract the imposed change. So what do you need for a buffer? Well, okay, what is a buffer? It's going to buffer against addition of acid and base. Now, it can't be completely perfect, but it's certainly buffering against it, hence the name. And you can see how it works in relation to Le Chatelier's principle. If you add strong acid, for example, the equilibrium moves to the left, and if you add base, the equilibrium moves to the right to try and counteract that imposed change. And that's basically what a buffer is. So the best buffers are those where you have more or less an equal amount. You have an equal amount of a weak acid and its conjugate base. Now, there's no point having a strong acid here because you don't get this nice equilibrium going on. It's more or less in one direction. So you want to have a weak acid and its conjugate base, and that way it can buffer both ways. Okay, so I'm now going to go on to the Henderson-Hasselbalch equation. Now, I'm actually going to do that as a separate section just to make it easier for you.